This equation changed the world, but I think it's taught completely backwards. Here's a real question. Why did physics even invent force? Everyone knows F is equal to ma, but nobody asks the important questions like why does that equation involve force? Why only mass? And why only acceleration? By the end of this video, you won't just remember the equation, you will understand why it couldn't have been anything else. I want you to forget everything you know about the world and physics. Forget Newton, forget force, forget the equations. Your task is simple. Just look at the universe and observe. You immediately notice one thing, that everything exists somewhere. This pen is here, the chair is there, and everything occupies a location. But how do we communicate where something is? This brings us to the very first idea of this video, that is position. Without position, we cannot describe the universe. Now observe the same chair a little later. Sometimes nothing changes. Sometimes it does. The object is no longer where it was. Say the chair has drifted. The difference between these two positions is called displacement. Notice that this is the first time that we are describing motion. And that brings us to the second idea, that is displacement. But is this enough? Imagine two runners, both cover exactly 100 meters. The first one reaches in 10 seconds, the next reaches in 60 seconds. Something is missing, right? It clearly shows that one runner has moved faster. But what is the missing element? Try comparing displacement with time. And that gives birth to a completely new quantity called velocity, which is how rapidly a position changes. Say in the first line, the runner is running with a constant velocity. In the second, he has started initially with a lesser velocity, whereas later on, he has moved slower. So that means, or it suggests that velocity has changed, and velocity cannot complete the story. We need one more quantity, and that is the rate at which velocity changes, which brings us to the fourth idea, that is acceleration. We have become very good at describing motion, but we have explained nothing. For example, why does velocity change? Why does acceleration happen? Or for that matter, why doesn't every object simply continue doing whatever it was already doing? See, till now we have identified a particular quantity, for example, position, which tells us where something is. But since that's not enough, we also want to know how much it has changed. So we introduce displacement. Similarly, how rapidly velocity changes gives the idea of acceleration. But why is acceleration changing? And what is the cause behind it? That becomes the one of the questions that physics cannot ignore. Say you interact with two different objects. You interact with it, it begins accelerating. You interact more strongly, the acceleration increases. You interact gently, the acceleration decreases. Interesting, right? That acceleration seems to depend on how strongly we interact with an object. But then say you're interacting in the same way and one object moves easily whereas the other barely moves. The interaction was same, however, the acceleration wasn't. Notice that some objects resist motion more than others, and we call this resistance as inertia. And to measure inertia, we invent another quantity called as mass. That is the next idea. Mass is measuring how difficult it is to accelerate an object. The greater the mass, the greater the resistance, and smaller is the acceleration. If interaction becomes stronger, acceleration increases. If mass becomes larger, acceleration decreases. At this point, the interaction itself deserves a name, and we call it force. But notice something beautiful. We didn't invent force first. We discovered force because acceleration demanded an explanation. Force is simply the name that we give to the interaction that changes motion. Replacing interaction with force gives F is equal to or proportional to ma. Finally, we define one unit of force, that is 1 Newton, as the force required to accelerate 1 kilogram by 1 meter per second squared. That choice makes the proportionality constant equal to 1, and one of the greatest equation in science emerges. F is equal to ma. Notice the journey we took. We never once assumed that force existed. We never memorized an equation. Instead, each new idea emerged because the previous one was not enough. Position allowed us to describe a location. Mass explained why different objects resisted or accelerated differently. Force explained why acceleration happened at all. And from these simple observations, nature revealed F is equal to ma. This equation wasn't the beginning of physics. It was a logical conclusion of careful observation and logical reasoning. A deeper secret lies inside this equation. Notice that if we replace acceleration with its definition, that is rate of change of velocity, something even more fundamental appears. That is Newton's true second law, and that is what we'll discover